So we start chapter 1 by looking at what a linear equation is. Now we'll recall that if we write something of the form ax plus by plus c equals 0. Now here the variables are x and y, okay, the last letters of the alphabet. The first letters of the alphabet will stand for constant. So I can write the equation like that, or I can write it in many different ways. Those are the two most popular ways. Of course, I could switch also the by on the other side and do all kinds of stuff, but usually that's how we're going to write down our equation. So that's we saw that's the equation of a line, right? Is the equation of a line in R2. And we know also that a and b are the coordinates of a vector that's perpendicular to the line. For example, right, I could write 2x plus y is equal to 4, and that's basically the line passing through, well, just need to figure out 2 points maybe to draw this line. If I set y to 0, x is 2, so this is 2 here, and if y is 0, if x is 0, y is 4, so it looks like that. Okay, that's my line. And what happens if I add over here an extra term? If I add something times, some constant times z. Well, we saw that the generalization of a line, especially when it's this is close to point slope form, right? It would be like point slope form expanded somehow. Well, if we extend the concept of a line in that case to R3, we're going to get a plane, because now ABC is going to be a vector that's perpendicular to the plane. So let's write that down. So maybe let's go through an example. If we have this equation, for instance, okay, it represents a plane, remember, since I can describe this plane in many different ways. I could say I could find a point, right, that belongs to this plane. For example, I could set x to 2, in which case y and z are both 0. Maybe the other way around, actually. Set y and z to 0 and solve for x, you get x equals to 2. And a normal vector is obtained by looking at the coefficients of x, y, and z. Right, so it passes through 2, 0, 0, and it's perpendicular to 2, 4, 1. If I want to graph this, it's not really helpful because it's going to be kind of complicated, right? Having something perpendicular to 2, 4, 1. What I prefer instead to do, if it's possible, is to obtain the points of intersection of the plane with the x, y, and z axis. So on the x-axis, for example, y and z are both 0, in which case x is 2, so 2 here. When x and z are 0, y is going to be equal to 1 here, and z is 4 when both the x and y are 0. Okay, so it passes through these 3 points. So if I join them, you can kind of see my plane here, right? So you can see that there's this plane here. Well, it's actually part of the plane, right? It's just a triangle that's part of the plane, but extended in all directions, and here's your plane. So this is just a reminder that these equations, right, represent either lines or plane in R2 or R3. So in general, equations of the form, so this is what we had started with, ax plus by equals to c, that'd be a line in R2, ax plus by plus cz equals to d, that'd be a plane in R3, but I can keep on going like this, okay, and now I'm gonna switch to x1, x2, x3, because I don't know how many variables I'm gonna have, but maybe let's say I have 4, and I don't want to use you know, x, y, z. Maybe I could use w, but let's say I don't want to do that. I could use x1, x2, x3, x4 for my variables, and I could use a1, a2, a3, a4 for my constants, and maybe b for the constant term. And in general, I could just keep on going like this and say, okay, this goes all the way to an xn equals to b. Okay, so those are called linear equations. Of course, it could be written differently. Maybe the c could be over there, maybe the by could be on that side, but at least when I remanipulate everything, I could set them up in this way. So those would be what we call linear equations. So maybe just let's go through a list here. Let's say I have this. Square root of x plus 3y is equal to 4. Now, is that a linear equation? Well, let's take a close look, especially at this term, right? This is not a constant times x. So what you should actually see here in general is you always have a constant times x, or a constant times a variable, and those terms are added up. So there are no special functions of x that you find in these equations. So root of x is not something you find in the equations above, and because of that, that's not a linear equation. So this is not what we would say is a linear equation. That's because of the square root of x. There's, however, the 3y. Okay, that'd be a linear term, but the root of x is not so combined together. It's not a linear equation. Let's look at another one. 3x, so that's a good start. Plus 2y, great. Minus 1 over z. Oh, no. See, that's not linear because of that term. The 1 over z is not something that's allowed in a linear equation. So this is not linear again. And this time it's because you've got a 1 over z. Be the same, right? If I instead write z to the minus 1, same thing, right? It's the exact same thing. You'd say it's not linear because of that. If you've got x squared plus xy equals 1, here it's not linear for 2 reasons, right? We're not allowed to have an x squared, and we're not allowed to have a product of variables. So if you've got a mixture of x and y multiplied together, or 2 variables multiplied together, that's a no-go. You can, well, at least if you want to be linear, that's not allowed. If I've got 2 to the 3 times x plus root of 7 times y is equal to pi, well, let's look at each term here. 2 to the 3, is that a constant? Actually, it is. Actually, we could rewrite this. This is actually 8x, right? So this is completely linear. Root of 7 is some number. I don't know what number that is. It's well, it's between 2 and 3, but it's 2 point something. But it's some number times y, so that's also linear. And pi is a constant, so this one is linear. This is linear. Okay, so that's actually the equation of a line in R2. And if I write 3y equals to 6 minus 4y, well, that one, is that linear? Yes, it is, right? See, I can write 3x plus 4y equals to 6. So like I said, you can rearrange this, and you can actually totally see that it's linear. I don't even need to rearrange anything. In fact, you know, as long as you've got constant times your variables, and then you're good. Okay, so this one is linear as well. And that's it. It's that easy to decide if it's something's linear or not. There's some properties actually that linear terms satisfy. I could have defined it this way. I thought I'd just go with something a little more informal. So in the book, this is basically all you'll have to do. You'll have to look at the equation and decide if it's linear or not, and try to mention why, like I did here, like identify the term that makes it non-linear.